enthalpy of, we can look at enthalpy of formation or enthalpy of reaction, but enthalpy is just a fancy type of heat. Enthalpy is it is essentially heat at constant pressure. So heat done at a normal atmosphere. But the idea here is we can look at enthalpy for any given reaction. A heat of a formation is the energy required to form any compound. We look at from its starting elements. So if I wanted delta AH of CO, this would be, you'd be the energy to do this reaction. Carbon plus 1/2 oxygen goes to CO gas. This is the one time we're allowed to have fractions in here because we want the enthalpy of formation of one molecule of CO. If I talk about the enthalpy of formation of, say, something more complex like sugar, C6H12O6, that would be 6 carbons, 6 hydrogens, and 3 oxygens going together form our sugar, C6H12O6. Sorry, off the screen again. Do that a lot. That would be enthalpy of formation when we're looking at that. Because of the way we set this up, the enthalpy of formation of any pure element is going to be 0. So if I went from carbon solid to carbon solid, these two numbers are going to be the same. And so this has to be 0 because some number minus the same number, if that's 2 and that's 2, 2 minus 2 is going to be 0. It doesn't matter what the number is. Any number minus itself is 0. The only way this is not 0 is if you're making something new. Say, O. Like if I go from O2 to O, this guy is not 0 because this is not a pure element. That's not how oxygen typically appears. And so while this is possible to make, it is not 0. But oxygen making itself is 0. Same thing, if I went from carbon graphite to carbon diamond, those would be different and those would have energy. But carbon graphite to carbon graphite or coal to coal is not going to change. To calculate our delta H for a reaction is just going to be literally the sum of the delta H of the reactants, of the delta H of the products, minus the sum of the delta H of the reactants. So products minus reactants. Final state minus initial state. Final state minus initial state. Because it's a change. But products minus reactants. If I were to do something like CH4 plus oxygen, let's see, goes to CO2 and 2 waters. How I would calculate this is I would have a number for each of these guys. I'd have a number for each of these guys, and I'd have the delta H formation of water times 2 plus the delta H formation of CO2. I'll take the sum of that. I'd subtract it, the delta H formation of methane and the delta H formation of oxygen times 2. However, we already know that one is a big whopping 0 because oxygen is a pure element. But so I'd look up these values. on most tests, you'll be given these values, and you just have to take the sum of these guys. You have to set it up correctly. Set it up correctly. However, you have to match them identically. If this is water liquid, this better be water liquid and not water gas. Water gas has different energy than water liquid. CO2 solid, CO2 liquid, CO2 gas all have different energies. So you have to make sure you use the right numbers, the right state. But enthalpy of formation is relatively easy. Now, one other thing that can be done with enthalpy is an understanding of Hess's law. Hess's law is basically a law that looks at what it means to be a state function. The idea that whatever I do to equation 1 and equation 2 to get equation 3, I must do to our delta H. This is an example that comes up in a lab, that I want this hypothetical reaction, C2H3O2 goes to H plus and C2H3O2 minus. However, the percent yield of this, the actual yield of this is incredibly low. This is a weak acid, a weak electrolyte. This doesn't break apart. And so trying to calculate the delta H of that is not practical. And so what we do, we go about measuring two separate reactions. We say HCl aqueous and NaOH aqueous go to water, liquid, and salt. When we break that down into the net ionic, it becomes H plus aqueous, OH minus goes to water. We'll say this has a number of negative 52 kilojoules. And then we look at another reaction. Instead of HCl, we look at acetic acid and sodium hydroxide. Goes to water and a salt. Though because of the nature of the weak acid, it actually simplifies to this. Aqueous goes to water and this. Now, we'll just say hypothetically this is negative 48 kilojoules. Okay. Oh, I'm off the screen. I need to stop doing that. Okay. To get this equation up here, I have to use this equation and this equation. So Hess's law says I can use these two equations to get this guy if I just pay very careful attention. If I look here, the identical parts that match up are these two parts and these two parts. They are as written correct. As written, they are the same. So let's go ahead and write those down. HC2H3O2. Go ahead and write the whole thing down. Water and C2H3 minus. Now, this H plus is only here. It's only here. However, you'll notice the H plus is on the right and the H plus is on the left here. So that means I have to flip this whole equation around. Flip this whole equation around. So rewriting this backwards, H2O, H plus, and OH minus. Now that they've added together, I cross off everything that is identical on both sides. And what are we left with? This guy, that guy. So when I calculate my delta H, what did I do? I added our negative 48 to, we flipped it, so we add it to a flipped negative 52. Flipped negative 52. So when I flipped it, I flipped the sign. So it becomes positive 52. And this particular problem, you would have positive 4 kilojoules as the result. So Hess's law says whatever I do to one equation and the other equation to get the third equation, I do to the delta H's, and I can find that is the delta H. And that is essentially what you have to do. That's what Hess's law states in one way or another.